Hello and welcome back to Mr. Powers Teaches Algebra. Today, right now, we're still going over transformations on graphs, and I want to look at vertical stretches and compressions, or stretches and I don't know, squeezes. So I got a little bit of I copied this out of this online book. Here's the address, and I just want to take a look at this. All right, and it's pretty straightforward. It's pretty easy, and again, I'll try to make as much sense of this as I can for you. It's a very good graphic we have here, and we're going to do a little on our own. So, oh, okay. Actually, that is a little bit of an explanation, but I'm going to do that later. So you can read that on your own time if you want. But here, let's say we had a function f of x. This is dark blue. If you have 2 times f of x, what you're doing is you're doubling every y value. And so you're making the y values that were there before get bigger twice as fast. And so it's almost like you take this thing and you stretch it. If it was getting large, it's getting large faster than it was. If it's getting smaller, it's getting even smaller than it was before. And then because you multiply something by 2, it gets bigger. And then what if you put a 0.5 in front of it, a half? Well, when you multiply a half or any number less than 1 times another number, you're getting something smaller. So now it's not getting as large as it used to get, and so that's your compression. So the 2 times f of x would be the stretch, a half times f of x would be your compression. And that's kind of how it works. And so we'll play around with that a little bit right now and try to make sure we understand how that works. So here's the deal right here. Here's what we want to memorize and know. Given a function f of x, a new function g of x equals a times f of x, where a is a constant, is a vertical stretch or vertical compression of the function f of x. If a is greater than 1, the graph will be stretched. And we might want to make a note here that it's actually really if the absolute value of a is greater than 1. And I think I'll go ahead and make that change here. If the absolute value of a is greater than 1, then the graph will be stretched. If the absolute value of a is between 0 and 1, it'll be compressed, because when you multiply something by a number between 0 and 1, it gets smaller, right? So that's going to be the compression. And then if a is less than 0 here, it says to combine a vertical stretch compression with a vertical reflection. So what we'll just, since I'm using absolute values here, we can ignore this. Okay, and we talked about reflections already, all right? So if a is negative, that's negative in front of f of x, that's a reflection over the line y equals 0. That's a reflection over the x-axis. We already know that, so we won't worry about that. What we'll worry about is just whatever this is in front of it, take the absolute value. If it's greater than 1, we're getting a stretch. If it's between 0 and 1, we get compressed. Okay? So with that out of the way, let's see if we can mess around with this and see what happens. So let's go ahead and say, and because we usually like to use a here, we'll say a times f of x. And there it is. We have g of x was our new a times f of x, and we got a little slider right here, so we can move this and we can see what happens. As a gets bigger, we get stretched. If we get between 0 and 1, we can see that kind of it's getting pushed down, and if we go negative, of course, it's getting flipped. And it's the same deal. And so that's looking at x cubed. Let's look at x squared. Take a look at that. So now the green is f of x equals x squared. And the orange, and actually let's make that orange a little bit bigger, make it a little easier to see. The orange, now with a parabola, you can see it very easily. Let's go with 2. Numbers are getting bigger twice as fast, and you can see that. 1 squared is 1. Where I had a 1 here, double it, we get 2. Where we had a 2 comma 4, 4 high, now it's 2 comma 8. We're making those values larger faster. And if we wanted to also, we could look at these tables of values, and you can see 9 versus 18, 4 versus 8, 1 versus 2. All those values are getting twice as big, twice as fast. And if I had a value between 0 and 1, like 0.4, now they're only 0.4 of what they used to be. And of course, you looked at the table. 0.4 of 9 is 3.6. 0.4 of 4 is 1.6. 0.4 of 1 is 0.4. So it's getting compressed on that case. And if we go further, of course, negative, it gets flipped because you have a negative, in this case, negative 0.5 of x squared. That's what our orange is right now. The negative is that reflection, and then 0.5 is the compression. We can go negative 1 is just simply negative x squared, so it just flips it, but negative 2 means it's flipped, and those values are getting, again, the traveling along that y twice as fast as they were before. So there it is. That's our vertical compression and stretching. All right, and I think that's probably a good enough show for you. Hopefully that makes sense. And it's one more thing that now we got to remember. And there's a lot there. And we could put it all together, and that's fine. So in any case, make sure you know these, and these are all the ways we can transform a function. Until next time, enjoy doing math.